Something fascinating happened during the Great American Eclipse in August of 2017 in the Earth's upper atmosphere, and scientists have only just now recognized this bizarre phenomenon. They discovered that the eclipse actually left a wake in the atmosphere as if it were a ship moving through an ocean. It's the first time scientists have ever detected such a thing, although it has been theorized before. Researchers at the Massachusetts Institute of Technology and the University of Tromsø in Norway detected the waves in the ionosphere. By passing in front of the Sun, the Moon blocks heat from reaching the Earth, and as the Moon moves out of the way, it creates a bow wave effect that acts as a ripple through the atmosphere. A huge network of global navigation satellite system receivers enabled scientists to detect this phenomenon for the very first time. We were looking at some phenomena that were expected but never had the chance to be observed, study author Shunrong Zhang from the MIT Haystack Observatory told Gizmodo. That was the surprise we found. We had a large coverage and our system is sensitive enough to be able to see these smaller variations. That was really very interesting to us. The abstract from the paper follows below. During solar eclipses, the Moon's shadow causes a large reduction in atmospheric energy input, including not only the stratosphere but also the thermosphere and ionosphere. The eclipse shadow has a supersonic motion which is theoretically expected to generate atmospheric bow waves, similar to a fast-moving river boat, with waves starting in the lower atmosphere and propagating into the ionosphere. However, previous geographically limited observations have had difficulty detecting these weak waves within the natural background atmospheric variability, and the existence of eclipse-induced ionospheric waves and their evolution in a complex coupling system remain controversial. During the 21st of August 2017 eclipse, high-fidelity and wide-coverage ionospheric observations provided for the first time an oversampled set of eclipse data, using a dense network of global navigation satellite system receivers at 2,000 sites in North America. We show the first unambiguous evidence of ionospheric bow waves as electron content disturbances over central eastern U.S., with 1-hour duration, 300 to 400 km wavelength and 280 milliseconds phase speed emanating from and tailing the totality region. We also identify large ionospheric perturbations moving at the supersonic speed of the maximum solar obscuration, which are too fast to be associated with known gravity wave or large-scale traveling ionospheric disturbance processes. This study reveals complex interconnections between the Sun, Moon, and Earth's neutral atmosphere and ionosphere, and demonstrates persistent coupling processes between different components of the Earth's atmosphere, a topic of significant community interest. The following is an abstract from a paper from 1976 on the phenomenon. Reference is made to Chi Monnet and Heinz J. Geophys. Res. 758751970, who suggested that during a solar eclipse the cool shadow of the Moon moving with supersonic speed through the Earth's atmosphere should generate bow waves. Upper atmospheric disturbances having quasi-periods of about 20 minutes were recorded after the eclipse of March 7, 1970 and were regarded as possible verification of this suggestion, but observations following the eclipse of June 30, 1973 did not detect such disturbances. The eclipse of October 23, 1976 will provide another opportunity to attempt to record eclipse-generated atmospheric disturbances. As a result of the curvature of the eclipse path and variations in speed of the Moon's shadow, the focusing of waves should occur at calculable positions and times. An enhanced amplitude and a focal region should provide optimal conditions for certifying the existence of a bow wave. Calculations are here made of the form of the bow waves expected for the eclipse of October 23, 1976, including the positions and times at which focusing effects are expected. Here's how the Smithsonian Institute describes bow shocks and bow waves. Bow waves in water create drag force that slows down the object, and in the case of large ships, can pose a risk to smaller boats, especially in a harbor. Streamlined shapes, mimicking those found in nature, are designed to produce as small a bow wave as possible. An object moving through the air, or the rarefied gas in the solar system, or intergalactic space, creates a series of pressure waves, or sound waves. When the object travels at the speed equal to or greater than the speed of sound in the gas, these waves merge into a three-dimensional bow shock, or shock cone. The width of the bow wave or shock cone depends on the speed of the object. The faster the object travels, the narrower the cone becomes.